That means while it's moving to the right, the left side is going to be bigger. The left arrow should be bigger, causing it to slow down and accelerate to the left while it's moving to the right, causing it to slow down. And if we look at each of our choices, choice C and D show it's in equilibrium, so that's not true. Between A and B, we need to look at the left side. Force of friction is the force that opposes your motion and it slows you down. So if friction is bigger, then it should slow you down. So it's not A, it's got to be B. Now, number 3, inertia is related to mass. So the greater the mass, the greater the inertia. We're looking for the one with the least inertia, so it's got to be the least mass. Choice D. Speed has no effect at all. Number 4, when the sum of all the forces acting on a block on an inclined plane is 0, that means F net equals 0. That means we're in equilibrium. That means we're either at rest or constant speed. So it's not B or C. Between A and D, A is saying it must be at rest. So it has to absolutely always be at rest if F net is 0. And that's not the case. It's not always true. It may be moving at constant speed. So choice D is valid because it allows for us to see that it can be constant V or something else, which is at rest. Now, number 5. Which mass would have the least acceleration if you apply the same force to each object? So you have, let's imagine you have a mouse and an elephant, and you push them with the same force. So the mouse being lighter is going to have the greatest acceleration versus the elephant being bigger is going to have slower acceleration. So the one with least acceleration is going to be the one with the biggest mass. If you're keeping force constant, keeping the same force. Number 6. So we have this force of 12 newtons pushing a total mass of 3 kilograms because both blocks are being pushed by 12 newtons and so they share the same acceleration. So F net equals ma, 12 newtons equals 3 kilograms times A is equal to 4 meters per second squared. So regardless if you're just focusing on block B or block A, they share the same acceleration because they're being pushed together. Now number 7 here. We got 25 being pulled up and 35 being pulled down. So that means our net force is 10 newtons. You'll have a mass of 15 kilograms, and we're looking for A. So 10 equals 15 kilograms A. A is equal to 0.67 meters per second squared. Choice A. Alright, number 8. A 4 kilogram object accelerated at 3 meters per second squared north by an unbalanced force. When you apply that same force to a lighter object of 2 kilograms, we're figuring out the acceleration. So 4 kilograms times 3 meters per second squared equals 12 newtons. Now, when you apply that same 12 newtons to a 2 kilogram object, we're figuring out what A is. So 12 divided by 2 gets you 6. Number 9 here, there's going to be a question on the test just like this, and it talks about Newton's third law. So action-reaction. And the way they word these, especially on the regions, you're going to focus on 2 objects, object A and object B. So in this question, we have a horse and a cart. The horse exerts a force of 60 on the cart. Now we're looking at what the cart exerts back on the horse. The cart exerts on the horse. So it's the same 2 objects, the opposite direction. So equal in magnitude but opposite direction. Newton's third law, action-reaction. So you need to keep in mind and look out for which 2 objects they're talking about. Number 10 now is about the difference between mass and weight. So remember that weight is dependent on gravity. It's dependent on the location. So weight changes wherever you go, especially going between different planets. Mass doesn't change unless you lose a body part on the way to the moon All right, so mass never changes. It stays constant wherever you go. Choice A, showing that it's constant. Following that same idea, number 11, so it's saying you have a spacecraft that is 20,000 kilograms on Earth. Now, if you're 1 Earth radius above the Earth's surface, what is the mass? Should stay the same, still B. Now, we're looking at the acceleration due to gravity on a place that's not Earth. So G is 9.81 on Earth. If you're somewhere else, it's going to be given to you, or you have to solve for it. So here, Fg, which is the weight, is equal to mass times G. So the weight is 45 newtons equals 15 kilograms times G. G is equal to 45 divided by 15, and that's 3 meters per second squared. Number 13, same idea, we're still on a different planet. 25 kilogram object with an acceleration due to gravity of 2 meters per second squared. We're looking for weight this time. 25 kilograms times 9.8, oops, not 9.81. I made a rookie mistake. Times 2 meters per second squared equals 50 newtons. So that's the weight now on this distant planet. Actually very light compared to Earth. Number 14. We have an object. 12 Newton horizontal force is applied to the object, which is at rest. So because it's at rest, it's in equilibrium, which means the force of friction to the left is equal but opposite to F. So if F is 12, that means the force of friction to the left is also 12. 15. Now drag force is the same as weight in this case. So they're equal in magnitude but opposite in direction. So Fg equals drag force. And when this happens, we are in equilibrium. So now that we're in equilibrium, that means we could either be at rest or constant velocity. So if you ever gone skydiving, that means you're obviously going to be moving downward. And you're not going to slow down. You're going to be moving at a constant speed because these two forces are equal and opposite. So it balances out to be in equilibrium. Alright, now we got to look up on the reference table which road surface would offer the least traction. So this means least friction. And voila, I brought out the approximate coefficients of friction table directly from the physics reference table, which you're definitely going to need to use during the test. So we're looking for the one with the least friction. That means these coefficients, we're looking for the smallest one, because the smaller the number, the less friction there is. The higher the number, the more friction there is. So for rubber tires, so rubber on dry concrete, dry asphalt, wet concrete, wet asphalt. So we're looking for the one with the smallest number. It's right here out of these four choices. Oopsies. Right here, rubber on asphalt, that's wet asphalt, so it's choice D. So the same thing is going to happen here for number 17. Now we're looking for the one that would produce the greatest force of friction. Alright? So we're looking for the highest number, so it's definitely not going to be a wet surface, because they typically reduce friction. So between concrete and asphalt, concrete here, dry concrete, has the highest friction out of these guys. Okay. Now number 18 and 19 are for the honors class because they got to do 2D stuff. So we're looking for the vector that represents the force that will produce equilibrium. So we're looking for the equilibrium. So that puts this whole thing into equilibrium. So this here is our net force, the combination of the two vectors. So we're looking for the equilibrium, which is the equal in magnitude but opposite in direction. Choice C. Applying the same idea to 19, net force is this way, equilibrium is the other way. But we need to figure out what's the magnitude using Pythagorean theorem. So a squared plus b squared equals c squared. 20 squared plus 20 squared equals c squared. So we're looking for the square root of 800. And you should get something that's approximately close to 28 newtons. And because our net force is northeast, that means we're looking for southwest as our answer. 28 newtons southwest. All right, number 20 is just like number 9, Newton's third law, except we don't have numbers. So the Earth on the moon is force F. Now it's looking for the moon back on the Earth. It should also be F. So no numbers, it's the same two objects, object A to B and object B to A, same thing. 21 is looking for the acceleration due to gravity, same thing, looking for G. So Fg equals mass times G. So I'm showing you guys what I expect to see when it comes to calculation work. So 45 newtons equals 15 kilograms times G. G is equal to 3 meters per second squared, and that's it. Okay, number 22, Jill is pulling a sled. That's 200 newtons with a constant velocity with a force of 10 newtons. This one's going to the right 10 newtons. It's moving at constant velocity, so it's equilibrium. That means this friction side is also 10 newtons. This weight going down is 200 newtons because they gave it to you in newtons. And the normal force is the same as the weight, also 200 newtons. So F of F, we're looking for the kinetic coefficient of friction, so that's mu. Looking for this guy. First, force of friction is 10 newtons equals mu times the normal force, which is 200 newtons. Mu is equal to 0.05, and that's our answer. No units. So something like this would be the expectation I want for you guys to show work. Alright, now number 23 and 24 are follow-up questions, so that means you need to answer 23 correctly to get 24 correct as well. But you're still allowed partial credit if you carry over wrong answers but follow the correct procedure, because at least that shows that you know what you're supposed to be doing. Okay, number 23, calculate the magnitude of the net force acting on the box. So net force, F net, equals mass times acceleration. Alright, we got our mass of 2.5 kilograms times acceleration of 2 meters per second squared, 5 newtons. Now this net force is the difference between the left and the right sides. Now because we're accelerating to the right, that means the left side is weaker, the right side is stronger. So if the net force is the difference between left and right sides, if the right side's bigger by 5, that means the force of friction here is just 10 newtons. There we go. Alright, my throat is really sore. I probably shouldn't have gone out shopping in the cold, guys, during Thanksgiving weekend. It was really cold. But I had to go to the outlets because it was really cheap prices. I got a really nice wallet, guys. Kate Spade had a 70% off sale. Anyway, I digress. My throat is killing me. Alright, 25 and 26. We are looking at a person with a weight of 850 newtons, along with the skis. F of G. Pushing back up is the normal force, that's equal and opposite to the weight, and that's what it's asking for, the normal force. So because the weight is 850 newtons, so will the normal force. Okay, now we're looking for the force of friction. The applied force and the force of friction, well, actually, doesn't really tell us much if he's accelerating or going at a constant rate, but we can solve for the force of friction anyway, given that the force of friction is equal to mu times the normal force. Do we have mu? Well, actually, we can look at the reference table, wax skis on snow. So let me pull that up in a quick moment. All right, let's put it over here. Okay, good. So wax ski on snow right here. Because the person is moving, we're going to focus on kinetic. Kinetic meaning motion, static meaning rest. Got it? Good. So mu is 0.05 times the normal force, which we already said is 850 newtons. 0.05 times 850 is 42.5 newtons. There we go. Now number 27, finally. Here we have a diagram below showing a 4 kilogram object accelerating at 10 meters per second square on a rough horizontal surface. What is the magnitude of the frictional force F of F acting on the object? So we're looking for force of friction F of F. Since the object is accelerating, it's not equal, not in equilibrium. So that means these two sides, F and F of F, are not the same. We can figure out the net force, though, with F equals ma. 4 kilograms times 10 meters per second squared equals 40 newtons. So that's the difference between left and right sides. Now, because it's accelerating to the right, that means the right side is bigger. This guy is bigger by this one by 40. So that means we can figure out 50 minus 40 equals 10. The force of friction is equal to 10 newtons. Yay, and we finally reached the end. Now here is a follow-up question for the honors kids, because you guys had to deal with 2D statics. So let me add in another slide in a moment. Now if you reach this point of the video, that means this is for you guys in the honors class, because you guys got to do 2D statics. Here is a practice question for you guys. So remember those hanging objects with 2 strings, 2 tension cables? Well, here's one for you guys. Let's say I have a 50 kilogram object being supported by 2 cables. Oh, that's ugly. Each set to the same angle of, let me say 25 degrees. Yeah, sounds like a really odd number. 25 degrees. So remember that when you have 2 tension cables set at the same angle supporting a weight, that means these 2 cables are equally sharing the weight of this object. So the weight of this, F of G, is being supported by the Y component, the vertical components of both tension cables. So T1Y and T2Y. Remember that vector components. This is in the reference table. AY equals to A sine theta. That's in the reference table. The same thing applies here. TY is equal to T sine theta. So we can figure out what's the weight of this object, 50 kilogram object, by doing 50 kilograms times 9.81. Okay? And you should get 49, oh, nope, not even. 490.5 newtons, okay? So that's the weight of it. Now this 490 is being evenly distributed between the 2 Ty components, okay? So T1y is the same as T2y, and they share each half of it, okay? So 490.5 divided by 2, you get 245.25 newtons. Okay, so each of these is carrying 245.25 newtons. That's your Ty. We need to figure out what T is. That's the ultimate question. What is T? So we're going to use this guy over here. So because they're both the same, you don't have to do it twice over. They're both the same. So 245.25 newtons equals T sine of our angle 25 degrees. divide both sides by sine 25, and you should get 580 newtons. There we go. That means each of these tension cables carrying a tension of 580 newtons, which is a lot. That's a lot of strain on those cables. Now, if you want to think about how you're going to reduce that tension, you're probably going to need to change the angle. So I'll leave that up to you guys to figure out how would you change the angle in order to accommodate for ease of tension in those cables. That's a follow-up for you guys.